Thank you, everyone. So this is part 2 of a talk that I gave back in 2015 originally, and we could skip forward to the next slide. If anyone wants to view the slides, they're available here. And I guess the impetus for the talk was that I guess when I was younger, I was always interested in, like some kids are interested in astronomy and, you know, the vastness of the universe and that sort of thing. And I had a similar interest in kind of like when I'd hear about gigantically massive numbers that I'd hear about. So it's just sort of this kind of amazing abstraction to think about. When I was a little boy, looking at, I had like a copy of the Guinness Book Guinness Book of Records, and they had a particular number, like the largest prime number known at the time. There were, you know, all these exotic names for different things, so I got kind of inspired by it. There was a lady, an Indian mathematician named Shakuntala Devi back in the day, who was famed for doing these really amazing mental calculations in her head. And at the time, she posed a question that I'd read about, where she asked, what was the largest number that you could write with 3 digits? And it turns out if you take like 9 to the 9th to the 9th, you get a number of like more than 300 million digits. So it's kind of, so that's just a basic thing. And there's like a Herman Cain joke in here that was actually kind of funny back in 2015. And it's still funny if you ask me, but so I'll stick with that. So the other thing that, there are other numbers that have kind of entered pop culture. The most famous one is Google, obviously, most via Google itself. That's 10 to the 100th power. Googolplex is 10 to the Google power, and googolplex is 10 to the googolplex power. So it's like 10 to the 10 to the 10 to the 100. And Google was coined by a 9-year-old boy named Milton Serrata back in 1920. His uncle was a famous mathematician and asked him to name 10 to the 100th. So just to get a little perspective, Carl Sagan estimated there were about 10 to the 80th power subatomic particles in the universe. So if you had to actually write out, actually this is Google. Actually Googolplex, if you placed a digit on each particle, you would literally run out of particles in the universe before completing your task. So you need like 100 billion universes of the same size in order to write out the digits in Googolplex. So then imagine how big like Googolplex is. So I had, so originally when I wrote this library, I needed to solve a problem that involved the divisors of numbers. And I used this library, this Haskell library called Arithmoi that does a lot of number theory stuff. And internally, he had a factorizing function which would represent numbers canonically. And what canonically means is to basically break things down into prime factors. So you have prime exponent pairs, and you'd have a list. So like 45 is 9 times 5. So you would write that as 3251, or 3 squared times 5. So, and each integer has unique prime factorization. So, and then once you factorize the number, it's a trivial step to find divisors. But I thought it'd be kind of a fun way to represent really large integers. So you could have simple things like, you know, what's 3 to the 10,000 times 5 to the 99th? And that would just be represented like this. So the whole idea is you're dealing with really massive quantities, but you're not actually directly calculating anything. So it's very easy when you multiply numbers like this. If you have common prime factors, you just add by group by prime factor. So you have this example where it's 3 to 1 power times 5 to the 99th. You just add like 10,000 to 11, and you add 99 to 2 if you look at the screen. So it's very trivial to multiply things. Division is the same way. You just subtract exponents or take the difference. And you know, of course, this is just really high school math. So, but it's just a clever little shorthand. But But then what came to mind was if you wanted to stick with this concept of representing numbers canonically, this trick wouldn't work the same way for addition and subtraction. Also you would have issues where, what if the denominator's exponent was bigger than the numerator's? You wouldn't have an integer anymore. How do you represent numbers that are still in that form? How do you handle negative numbers, 0? So there are just little things like that. Yes?
When to do addition, can't you just do at the max of the two? Wouldn't that be pretty close?
Well, because you still want to factor everything. So if you have, if you add like 1 to like a Google or something, right? Then you'd have to, you want to get it in the canonical form, which is like some list of prime exponent pairs.
A better example is your Mersenne prime. 2 to the power, we subtracted 1, you get only one ginormous prime now.
Right. So in that case, it would expand. It would write that out. It would just be whatever that expands to, comma 1. So, which to your point though is not very convenient. So, but it's kind of it's not a perfect solution for everything, but it's just the mode of working, I guess. Now this is some detail about how it's represented internally. It's just some simple Haskell stuff, but it makes use of something called a new type, and it's basically just the data structure that's used. You can kind of skip over that. So internally, if you were to look at the code, there's a file called internals.hs, which has all like the lowest level nitty-gritty stuff like prime exponent pairs. There's a simple file which imports this file that makes use of the internals file. So basically we use this simple Canon class as the type for the outside world, and we hide like the implementation details that are found in the internals file. So the interesting thing in Haskell is you have the concept of a type class. So if you want to create a number, you have a num type class, and there's various things that need to be defined. There's actually several different, so we'll go over num first. You have to define, you can basically say, well, this is what addition is, this is what subtraction is, this is what multiplication is, yada, yada, yada. There's also things for, you have to define what a comparison is. If you want real numbers, you need a two-rational function, and fractional is another type class. There's also, if you want to say a number is integral, you have to define two integer quote rem, which is sort of like when you divide a number and what the remainder is afterward, and also mod for modulus. So you take 5 mod 2, you get 1 left over, 1 is the modulus. So this kind of comes up later on. It's possible to do some very powerful things with mod, thanks to something that the mathematician Euler came up with a couple hundred years ago. So you can do things like, you can take an arbitrarily large number and easily say what are the last like 10 digits, that sort of thing. So, so going back to the earlier question about division, what do you do when you have something that's not an integer? You need to expand your definition to have like a rational number. So initially I thought, well, let me expand this to have this like rational canon concept and kind of create another new type. Sorry. But so I went down this rabbit hole for a while, and I realized that it's kind of pointless to have all these various types and that sort of thing. So I came up with this generalized idea, so that this is kind of the first insight to handle really, really large numbers. Still not psychedelically large, but large nonetheless. So what you have is, instead of having like prime exponent pairs, you have prime Canon pairs, and a canon can be basically it's like a recursive definition. So a canon can be either like a bare integer, like a prime number, or it can be something called like a list of prime Canon pairs. So it's like a definition that feeds back into itself. So I'll skip over that and do some like implementation details. So you can say like one thing to help with processing is to keep track if something is an integer, it's a non-integral rational, or it's an irrational number. So it's like if you raised a number to, you raise 7 to the 1/5 power or something, that would be an irrational number, or the square root of 2, something like that. So I'll go over that. This is some detail about bear. So basically, you keep track whether or not the number is factored or not, or if it's a prime number or not. Because sometimes if the number is too large, it may be too expensive to try to factor it, even though you know that it's not a prime. So you just indicate that it's not simplified. That's what NSEM stands for. And let's see. So this is like a little detail internally of what's happening. If you said, give me 11 to the 11th to the 11th power, internally it would look like this, admittedly sort of gobbledygook. Now, the interesting thing about this library is that you can't actually use the normal, even though like exponentiation is really important to it, it's critical to the library. You can't actually use the default operator. You have to kind of define your own to optimize what you're doing. I was wondering, does anyone have any questions? So one thing that really came about as sort of a mantra when I was developing this, especially when I kind of gave the enhancement to this for these hyperoperations, which I'll get to, was this idea of that like perfect is the enemy of good, where I would try to make something absolutely perfect, even if something would be like, say you had a really large composite number, and you knew that it was a composite, but it was too large. The library that you're using, it's basically impossible to factor. Maybe it would find the answer in 10 years, maybe never. So I had to put some things in so that I would kind of still be able to process things in a quick enough way and not have things hang indefinitely. So I put in like different cutoffs and that sort of thing so that it would be a little bit easier to use, and it wouldn't be that big a deal to not have, like a perfect answer. In some cases, when you're trying to, like say if you're trying to find the divisors of a number or something like that, if you didn't have a totally simplified number, it would just say, well, I don't have complete information about this number, so I'll just kick it out as an error because I'd rather, give an error than have it hang or give an incorrect answer. So that's kind of a little design tweak or mantra that came into play. So this is a list of different functions in the library, kind of common regular things like taking the reciprocal of a number, the greatest common divisor, the lowest common multiple, taking the numerator and denominator of something, and then there's some internal routines. Now one thing, this is what I was starting to go over earlier, the exponentiation operator. The really nice thing about Haskell is that you can define your own operators and you can basically do anything with them. So in this case, I had to create a new operator so that it would, and advise that it be used in place of the default operator for exponentiation, because it basically doesn't work. So if you use it the default way, because a lot of it is, with the exponentiation, is you can sidestep all the calculation, whereas if you use the default operator, it will actually try to go in and try to figure it out, and you'll have a long day waiting for things to come back. The other thing, it's kind of the inverse, is the root operator. So you can do things like take the example we have here is like 2, this funny operator 9 is like the square root of 9. If something isn't valid, basically it won't allow you to give you an irrational root, but it'll allow you to give like a rational root. So like if you try to take the 7th root of 9, it would give you an error. But if you try to take the one above it, you'd still get a rational answer. So it would allow you to do that. So this is where it starts to get into the psychedelic world. So There's this notion of like an arithmetic hierarchy of hyperoperations. So the first three are very common. Basically, level 1 is considered addition. So if you said like A plus B, that would be equivalent to adding 1B times to A, if you think about it that way. So, and similarly, whenever you go up to the next level, you do the previous step that many times. So if you said A times B, that's the same as adding A B times or B A times. And exponentiation, A to the power of B is equivalent to multiplying A B times. So if you said 7 cubed, that would be the same as 7 times 7 times 7. Now,
Sorry, but I don't understand the difference. A plus B and A plus B.
oh, it's A times B, the second one.
The first one.
Oh, okay. So it's like so say you add 5 to 3, right? So you have, or maybe you add 3 to 2, right? So you have your 3 fingers here, and then instead of just adding 2 to get 5, you add 1 2 times. So you get 4, and then you get 5. So it's just like a foundational thing to explain what the rationale is. So.
And you just want to base numbers on count.
Yes. So then the analogy, when you get up to multiplication, it makes more sense. You're like, oh, because nobody adds a number or adds 1 so many times, but multiplication, when you learn it, it's like, oh, you're really adding it that many times. So that's kind of the basics of math. And then the interesting part is what they call level 4, which is, that should be lowercase. So it's basically exponenting A B times, so, or the equivalent of that. There's no real word for that, but they call that tetration. And what that is basically like a power tower. So earlier when we were talking about the 999 number, so that would be like 9 tetrated 3, because you have 9 like a power tower of height 3. So that's what the analogy is for tetration. Does that make sense? Does anyone have any questions? Or, okay. So we just went over that. So we just started explaining about power towers. Now the interesting thing is you can see how rapidly the numbers grow with tetration. So when you start with 2 tetrated 2, I guess is the way to put it, you end up with 4. 2 tetrated 4, it's basically 2 to the 2, 2 to the 2 to the 2, 2 to the, 2 3 times, which is 16. And at the end, you get 2 tetrated 6, and they're still very small numbers, but it's 2 to the power of 2 to the power of 65,536, which is 2 to the 16th. So things grow extremely rapidly. And so then, even beyond tetration, it kind of uses that same root. You have level 5, we call that pentation. And that's equivalent to like tetrating something B times. Hexation is the same as pentating something, if you will, B times. So unfortunately, there's no words for, I'm not sure what the proper term is for these things. But the funny thing is that the nice thing about Haskell with the operators that you can define, I basically added like extra less than or greater than within the B, so they grow out and look basically progressively scarier. So that was intentional. So so you could see like down below, if you have 4 pentated to the 2. Now 4 pentated 2 is basically whenever you have 2 to whenever you do something 2 at a particular level, like 4 pentated 2, it's the same thing as the lower level and then that original number. So like x pentated 2 is the same as x tetrated x, something like that. So what we have is 4 pentated 2 is this massive number, 5 pentated 2 is this number with that's like much bigger than googolplex, whatever. It has more than 10 to the 10 to the 2814 digits. So, and again, this is still like kind of early on in what we're looking at. So what happened was, so we can go further because you can define anything you want in Haskell. There's operators in the library defined up to level 50, and there's sort of a naming convention for getting there. So like different characters are introduced, and it gets kind of silly by the time you get to 50. So, but seriousness is not the point here. So this is like the shorthand for how the operators are defined. So if you have something with a tilde in it, that stands for 10. If you have a vertical line, it stands for 5. And if you have the less than greater signs, they stand for 1. So we're up to level 50, which is great. But what if we want to go, why can't we just make things like the level arbitrarily high? So what I did was I extended that original definition of the Canon data type to have something called hx for hyperexpression. So that consists of a level of hyperoperation, like 50 or something, or 4 for tetration, then a list of operands. So you could say something like I'll show here. You could say, give me 5 tetrated to the 5 tetrated to 7 or something like that. And that would, internally, that would have just have an array of 557, but it would be associated with this level 4, this operator to do tetration like a power tower. So let me go back. And so that just explained that. So the interesting thing is there's operators defined for up to level 50, but there's also another function where you can actually pass in the level of the hyperoperation. So you can say, I want this to have level Google or something like that, or this 3 hexated to 5 or something. And this actually comes up, there's actually a point to this. Let me see. And one thing that I found was, because it actually, to do this correctly, there's a lot of details involved and like nasty edge cases and all that. So this can only be used for integers. So, because part of the, oops, let me see. Let me see. Does anyone have any questions? Or? So there are certain things you can do. You can negate hyperexpressions. You can just not have non-integers. Internally, it's sort of a optimization. So like if you have a sum, whenever you have a sum, it's always positive. But if you want to make it negative, you multiply it by a negative figure, and that just helps with the processing. So that's what this is basically. There's other things like if you actually raise certain figures like negative numbers to certain powers, you can do it, but it will actually distribute the sign or erase it if necessary. Like if it's an even number and you raise it to an even power, the negative sign will go away. The weird thing though is you can't, if you do something like tetration, so say you want to say -2 tetrated 4 or something, you can't do that because the answer may not be an integer. So that's kind of forbidden in this library. Let me see. So there's functions to indicate if something's a hypersum or a hyperproduct. These are some examples. So you could say this is 1 plus 3 pentated 5. This is 7 tetrated 5 plus 7 pentated 5. You can multiply things together, all that sort of stuff. So just like regular numbers. The interesting thing I found was that I really had to be strict in like keeping the ranges of the hyper numbers and the non-hyper numbers distinct. So it's almost like I called like an event horizon. So once you're beyond the event horizon, you're kind of in the hyper world. Anything below that, we either represent kind of in the old-fashioned way or just as a bare number. The interesting thing too is there's different things that come up at different levels of the hyperoperation, which I kind of learned on the way. If you go level 6 and beyond, like comparisons get much easier because you so much dwarf anything at a lower level, you don't even have to consider it. So like if you have a number that basically you can go by the maximum. If you looked at a big expression and the maximum hyper level was 7, and another one it was 6, you wouldn't have to compare anything else. You just know that the 7 was larger. Like basically, there's probably some pathological exceptions to that, but so it's kind of interesting now. The other thing is it goes up to level 100 in terms of like sometimes it has to drill, well, I'll get to that. There's another cutoff for actually doing more in-depth calculations. And there's a big problem, there were a lot of challenges that I found in terms of like avoiding the calculation versus actually delving into it and getting really specific with what I need to find. So this is where like kind of some of the algebra comes in. So if you give me, you know, the same expression and you add them together, it'll group it as 2 times the number. It'll collapse different things. So if you said this crazy number squared times the same crazy number, you'll get the crazy number cubed, that sort of thing. It'll cancel like common terms and that sort of thing. So there's a couple of, there's a few identities that come in place when you're trying to simplify these things. So for instance, there's something that I found useful to do in the code, which was the idea of demoting something. So if you have x with some hyperoperation and then 2, I'd try to demote it to x and then the previous level x. So for instance, if you said 3 times 2, that's equivalent to 3 plus 3. In the hyper world, if you said 3 pentated 2, that's equivalent to 3 tetrated 3. Does that make sense or something? Okay, and then there's the notion of what we call like an upgrade chain identity. So if you said, basically, if you said 3 plus 3 times 7, that's the same as 3 times 7 plus 1, or 3 times 8. So you basically use the same hyperoperation, but you just add 1 to the second term, the y. So if you did this similar expression with tetration and pentation, you would get pentation to the next level up. So it's hard to verbalize this, but 3 tetrated to the 3 pentated 7 is the same as 3 pentated 8. So things like that are useful within the code to simplify expressions, and also things like, you know, because it is a number, you have to be able to robustly compare things and that, check for equality and all that. Let me see. There's other things like if you had a chain like of, like this first one is like a power tower of 3 high. So this promotion identity would collapse it into tetration of 3 high. So there's another flattening example, which is into it.
Fred, how do you figure that out?
Well, how do you figure it out?
How do you figure it out?
Well, it's kind of by definition, actually. So when you have like for instance, you say 5 plus 5 plus 5, right? That's the same as you're taking 5 3 times and adding it. So that's the same as 5 times 3. So this is the analog except with exponentiation. So you have a power tower, but then you just say it's 3 high, so I'm going to give it the next higher level. So this level 4 tetration. Does it make sense?
It makes
Oh, how do you do it? Oh, like symbolically in the code. So you're,
Figure this out.
well, some things are pretty straightforward, and other things are really, they get pretty hard, like trial by error and stuff. Like comparing things, like arbitrary things is really hard. Ida will attest, my wife. So, which is a nice segue, actually. It turns out that, oops, when you do want to, when you're doing these different functions, you know, treating them like first-class numbers or whatever, it's really, really hard to compare them accurately. There's a lot of edge cases. It's a really complex problem. And then there's some things like if you want to find the greatest common denominator of things, greatest common divisor of things, or the least common multiple, some common problems that you need to find that were kind of easier in the old library. Like if you said, like for instance, if you said 3 to the 10th power and 3 to the 8th power, and you wanted to find the greatest common divisor, it would be the lower exponent, it would be 3 to the 8th. If it was the least common multiple, it would be the higher exponent, it would be 3 to the 10th, something like that. This makes sense. So then what happened was, when you're actually dealing with these higher level numbers, you run into something called the tail. So I had to create a function so like most of the time you're just dealing with the number at a certain level. So you say like this is tetration. I have like 3 tetrated to 10, something like that. And I just deal with that like as almost like symbolically. I don't really delve into it. But if for some reason you wanted to reduce it down to like exponent form, so you could do things like the greatest common divisor, least common multiple, you would have to use these identities. So like if you had x tetrated n, that would be the same as x to the power of x tetrated to the n minus 1. So it's kind of like if you had a power tower of n high, right? If you take, say, that x and raise it to the power of a power tower n minus 1 high, that's kind of the equivalent. Does that make sense? Like, so then what happens is tetration is kind of somewhat intuitive, but when you get to pentation, if you do something similar where you kind of reduce it with the previous level tetration and pentation of the n minus 1, that's the first step, but then you have to do it again to get down to exponentiation. You have to kind of like demote it down. And you might have a situation where like in this hyper world, things aren't really stored as prime. So like if you like for instance 6 isn't a prime number, but if you had 6 tetrated 5, you would now have like 2 different tails, like 1 for 2 and 1 for 3.
So if you get x pentated n by doing x up n times.
Yeah, you tetrate x n times. So
then how do you, if it looks like just x up n times,
right. Oh, that's a power tower. Yeah.
so then how do you go back down by like popping x's off and then get net minus 1s?
Oh, so
Is it
it's
still equal then?
it's sort of like if you said if you use the analogy of addition and multiplication. So say you had 3 times 5, right?
Yeah.
That's the same as 3 plus 3 times 4.
Yeah.
So if whatever, the interesting thing is whatever level you're dealing with, if it's multiplication and the previous level, or it's, you know, level 50 and level, that analogy still holds. So it's kind of, exactly. So, but the tricky thing is that it's, you know, it's intuitive to go like 1 level down, right? But when you go to pentation, you have to go 2 levels down to get to exponents. So you get like increasingly gnarly looking tails, which I'll get to. So hexation looks worse, level 7 looks worse, And then, for instance, let me, I don't know, define something level 83. So, yeah, brace yourselves. It's hard.
But you just use the previous definition? Like you leverage your previous code?
Yeah, it recursively goes down, and so this is, whoops. Yeah, so that's, so, yeah.
Can you put that on a t-shirt?
On what?
T-shirt.
On Tinder?
T-shirt.
I think so. I think for you, Matt. So then one thing that ended up being a lot of work was this idea of like taming the tail, I guess. So there's this function I was using to create this tail called like, I was calling it quasi-canonizing it. So that would basically, that would do it would break everything down either into prime factors and try to break things down to like the exponent level, or if you had some sum, like say you had 1 plus 5 tetrated 5 or something, and you raised it and you tetrated that or something, it couldn't expand that, so it would just leave the sum as it was. So that's why it's called quasi instead of canonizing. So there's this function called hyperize, which kind of does the reverse. So almost anything that you can put into it, if you've turned it into this form, it will reverse it. So, like, actually, I could try it. So hopefully this actually works. So if I took this thing, I think I'm setting myself up, but if I quasi-canonize this and get that big nasty thing from the slide, so I get this crazy thing, right? Now if I hyperize it, it'll return the original thing. So it'll roll it back up. And you could do that if you had like, if it wasn't a prime number, it'll do that too. So this will look even worse. But that's not really ready for prime time, so you could do that, and it'll inverse everything. So that was one of the biggest challenges in the code. So what can happen is when you're trying to do some accurate calculation for something, you might have to like go into the woods like that and then come back out. So this function, this hyperize function, will actually clean everything up for you, so it doesn't look like gobbledygook, so, or less so, There's one identity I found, it's probably not worth getting into, but anyways, does anyone have any questions? Or? I'm sorry?
Are you like testing this with your library? Like you have like property tests that like verify that this?
Oh yeah. There's a whole. It's not like formally in quick check or whatever, but I have a suite of things I've tested. But some things like this identity is actually algebraically you can show that it's true, but it's a very specific case. But it just happened to. The only problem was that like if you were to pipe it in. Oh, one time I piped something like this in, just testing different combinations, and I got a different result back. I thought, oh, that's really weird. And then I looked at it, oh, it's actually the same thing. So, or it's equivalent, I should say. So, oh, hi.
Are there like any branches of science that use this notation? You mentioned, like,
The notation, no. Sometimes there's
well, not your notation, but like this kind of, instead of like scientific notation.
Oh, hyperoperations.
Do they ever need such large numbers?
It does. Yeah.
Combinatorics where at least 2 arrows are shown.
Yeah, that's actually coming up. So, that's. Okay, so I don't know if this is too much detail, but there's a lot of different techniques you can use when you're comparing these things. It seems like a trivial thing, like, if you have two numbers, first class numbers, you should be able to compare them accurately. So there's something called superlog that was done, something called Domination, a few other ones. I'll just go over them one by one. Oops. So the superlog is kind of like, it's sort of like a multiple level like logarithm. And I learned in the meantime that there's something called an iterated log, which is very simple. So very similar. So it's kind of like you have a log, and it's basically like based on the power of 10, right? But if you wanted to, like for instance, Google is like 10 to the 10 to the 2, right? So your level, your mantissa, what's left over is 2, but your actually level of your log is also 2. So that's one way to compare these really large numbers. So it's sort of like in this case, it's like rounded up. So the number of digits in the number of digits is 2. It's really like 100 is the cutoff, right? So it's really 3, but it's like 2. You know what I mean? So like a level 2 log would tell you the number of digits and the number of digits, right? So
Height of the tower?
kind of, yeah. So if you went 10 to the 10 to the 2, you have 2 10s in there and then a 2 at the end. And then, so that would be, or if you had, that's Google. Googolplex would have 3 10s and then a 2. So that would be like 3 comma 2 in this world. So if you're comparing these crazy things, you can figure those out with some limitations. And then, like, what if you wrote something out and it said 10, 10, 10, 3, and the other expression was 10, 10, 10, 4. Oh, the second one is bigger just because of this iterative log idea. So this is kind of a slide that explains that. Oops. There's kind of a trick that you can do. It's probably too much to get into, but the complicated thing is that when you're dealing with these really gigantic numbers, like say you have that, like googolplex or whatever, and you multiply it by 3 or something, some small number, it will have very little influence on this multi-level log. So there's some subtlety to it and like what to ignore and that sort of thing. And the tricky part too is that even if you compute something and you have the exact same number, you can't really rely on that. But if one is greater than the other, then you can say, oh, I can rely on that. You know what I mean? Because there's so much like, basically like rounding error, like at a higher level. So okay, so now we're getting into domination. So domination's a pretty easy idea. So no matter what you have, say you have like these 2 tetration towers. Say you have 3 tetrated 5, tetrated 7, and 5 tetrated 11, tetrated 13. So, you know, both gigantic numbers. Oops, but at every level, every term in this list, in B, the term is bigger than the term in A. So you can say with certainty that must be larger. So that's an easy win, I guess, or an intuitive thing. There's another one that comes up where I was kind of struggling comparing some of these things, or preventing hanging and that sort of thing. And there's a related thing called sub-expression domination, which is if you have any, and this is helpful. This goes back. This makes things like restrictions, like only allowing integers, very helpful with this sort of reasoning. So you could say that no matter what you have, assuming the signs are matching, if one sub-expression, say there's some sub-expression of B that's bigger than A, then B must be bigger than A. So it's kind of an intuitive thing. So whatever crazy thing you have embedded in your expression, like some arbitrarily complex thing, one chunk of B is bigger than all of A, B must be bigger than A. There's another thing which is more intuitive, which is if you want to eliminate common sub-expressions. So for instance, and this kind of goes back to the domination bit, if you have this crazy expression involving 7 and then the same one minus some number, you wouldn't use like this sub-expression domination. You would eliminate the common term. So then it would be reduced to like comparing 5 tetrated 6 to 0. So something a lot more you basically kill the 7 term from both sides and add 5 tetrated 6 to both sides. Simple math like that. But if you had something where it was 7 hexated 7, and you were comparing it to 7 hexated 8, and then you cube that, the one involving 8 would have to be bigger because this sub-expression is bigger than all of A, if that makes sense. Then there's this notion of once you get to hexation, which is level 6, whatever the maximum hyperoperation you find in the expression, if one is bigger than the other, then that expression will be bigger. So that's kind of an interesting thing, because it's just such a like a order of many magnitudes bigger than pentation. So, oops, I did not mean to do that.
So that's a phase transition, you're saying?
Yeah, kind of, yeah. So that is a key point. So like once you get above hexation, if you're one more than the previous level or more, then you must be bigger. So, and that could be anywhere in the expression, assuming the assuming the signs are in alignment, you know what I mean? So one side's negative, one side's positive. The positive number would be bigger, but does anyone have any questions?
So what do you think it would look like if you were to graph something like these functions? Like say if the output is like the z-axis and A and B or x and y. What do you think something like that would look like?
Oh, like vertical.
What
Yeah.
if you scale it out enough? Is it just going to always go straight up? Because if you're saying that anything with that
It would.
6 is going to be automatically bigger, do you think something like that would be represented if you have
Oh, do you mean like if your z was the level of the operation to hyperoperation?
no, just
Or z, or I'm sorry. So x and y are, it would be x and then some hyperoperation and then y.
and then whatever that is equal to.
Would be z. Yeah, it depends. Like there's one funny thing where like there's different things I found where if you take 2 and then any hyperoperation and then 2, it's always 4. So that would be a straight line. So if you say 2 plus 2, 2 times 2, 2 squared, 2 tetrated 2, it's always 4. So that would be the exception. But other than that, it would be, so.
The more you zoom out, the less interesting it gets.
Yeah, yep. Well, it's either completely flat or, it's either horizontal or vertical. That's kind of interesting. So it's not very, and this is used in graph theory, so go figure, yeah. So let me see. Sorry.
In terms of the errors that you run into, are they thrown as errors, as exceptions, or do you determine?
Sometimes, like you catch something, like it just doesn't make sense, like you made a mistake in some way, and most of the time it just hangs, and then you turn trace on, and I had a problem at one point where I turned trace on, and when it was showing it, it was actually calling the same function, so that was a bad day, yeah. So that was painful. Yeah, so it's avoiding recursive calls like that. So let me see. The interesting thing too is like this going back to this hexation idea being kind of like a phase transition or a cutoff. If you compare two things, basically whatever the last item in the list is. So you have like this Google hexated 7 and 3 hexated 8. Just because you're dealing with hexation or more, and the last term is greater in the second in B than in A, B must be bigger than A. So that's kind of an interesting thing. So,
Is this proven or is this?
Well, it's well, there is. It's not. There's exceptions to it, yeah, but it's generally true, yeah.
Basically, you could defeat it if instead of Google, I put, you know, one of your 53rd order operations or
Right.
something like that in there.
Well, that's the thing. Then it would do the 53rd thing and say, oh, that's the maximum one. So you have to apply these checks in the right order. That's the tricky thing. So it's like once you've ruled out, you know, so the tricky thing is when you have things that are close to each other, like the same level, and you embedded things like that. So probably there's some other things that are done in that you kind of you can glom things together as well too. So it's even if you inserted something in, it would know. You know what I mean?
That's kind of what I was meaning with the graph, because if you graph something like that, theoretically you'd be able to see, you know, where the trends would be going.
Well, the thing is, when you increase y though, oh, in that sense,
You know, if you say like,
for a given y, it would be vertical.
yeah, but if you have x and y as ordered pairs, as in Google and then 7, and then 3 and 8,
Right, but it would still look like pretty much like a wall after the initial.
but then you know the answer to that just by assuming. Is that what you're trying to say, I guess, is that you assume that that's just automatically correct?
Well, it's one of those things. There's probably, like for this case, there's probably some number. There is a number where a very, very, very large number that would violate this. You know what I mean? And you can figure it out. So like at lower levels, there's a lot of logic in terms of that, so that you know, there's edge cases where you have to look for. I'm sorry. Yeah.
You understand what I'm trying to get at?
Oh yeah. Yeah. So, okay. And then this is alluded to earlier with the tail. So you can have an arbitrary level of hyperoperation, and this kind of. Now, beyond that, there's a few different functions for actually showing, for displaying these hyperexpressions in a more palatable way. Like by default, it factors everything, but sometimes that can be a headache. So you want things to look in a more, you know, you can run things in different modes so they look more simplified, and it's easy to understand what it's doing. So then. I guess maybe the next level after that was this new module called special functions. So going back to, I'm sorry, what someone was asking about what this was actually used for or how this came up. I was talking to someone at this meetup last year, and I was telling him about this library, and he asked me if it could handle Graham's number. And I was like, no, it can't. And I was really bummed because not even close, right? But
Can you tell us what Graham's number is?
so Graham's number with this handy slide. Yes. So basically, it was the largest number used in a serious mathematical proof. I think it was in the Guinness Book of World Records for a while. And Martin Gardner, who was a big guy over at Scientific American, popularized it about 40 years ago. And it's the upper bound related to coloring the vertexes of a hypercube. And it stems from a branch of math called Ramsey theory, which is like a combination of combinatorics and graph theory. And it's an upper bound for a proof. So So basically, there's several functions in this special functions library for handling Graham's number. So it's basically a recursive definition. You start off with hexation. So you have three, it involves three. So you say 3 hexated 3, and then it feeds back into itself. So you keep pumping in that same, the hyper level, the level of the hyperoperation keeps getting fed back in recursively. So what happens is, I'll show you, you get this crazy nested definition 64 levels deep. Oops, Graham's number. There it is. So internally, let me see, somewhere in there, you have, boy, it's like a Where's Waldo thing, but there is like a hexation embedded in there. Oh, you do see, oh, there it is, right in the middle. That would make sense, it's right in the middle. So you can do things like, so for instance, you can say, you know, so you can do math with it. So you can say, give me Graham's number tetrated to Graham's number. And then you say, let me see. And then you say, give me Graham's number tetrated to 5. And then you say, okay, give me the greatest common divisor. Oops, same variable name. That wouldn't help. Let's see.
V and X are not the same.
Oh, yes, you're right, sorry. V and X, okay. So then you say, okay. Oops, oh, tetration's not good, sorry. To that power, okay. And I'll say X. Yep, so it found it, so. And then you say, give me the least common multiple. It'll do, so it'll do stuff like that. And then you say, I don't know. Let me see, Graham's number. Oh, how about this? V times V. So that will take that and square it at some, actually, it's not very clear. You see the 2? Okay. I know it works. Okay, so if we do, oh yeah, so it's Graham's number, and then to the square of Graham's number, or to the power of 2 times Graham number. If you say V plus V, you have the 2 in front. If you say 5 times V minus 3 times, or minus 2 times V, it'll give you 3 times the number. So it'll just do normal math with it. You know, to some point. It's still a little weird with like tetration and stuff. It's really not. But you can do things like Graham's number, what are the last 10 digits, right? They'll figure that out. Oh, and that factors it, but. So if you were to look that up like in Wikipedia, that would be the last 10 digits. So you could do like this crazy V thing. I think actually maybe X, yeah. If I wanted the last 10 digits of the 5th power of the Graham's number, stuff like that. So, and then you would just show UNF. So this just shows things as is, this function, like show unfactored. So that would be the last digits. So it's kind of fun. You can just do pretty much arbitrary math with it. So does anyone have any questions? Or?
So what's the biggest prime number you can show this way? Is that limited by the computer? Or how do you
Oh, prime number or? Oh, well, if they're primes, then you can they're just primes.
What about that big percent prime?
Well, that you can do that with, it'll support it just like big number math in whatchamacallit, in Haskell. So like this number, so it'll do that.
But what about the prime, like the next prime above that one?
Two to that
Like
and minus
theoretically.
one.
Oh, you know, it's so I say this, right? And then I say,
It's crazy how it turned out that big.
and that's just regular Haskell actually. But then I can say, well, how about I say, oh, well, that's a good point. So now I'm going to say, give me 2 to that power, right? And, oh, because it has to figure it out. Oh, no, what it does, no, it doesn't actually factor it. So the reason why it has its own exponentiation operator is so it doesn't do anything. It just says, oh, okay, I'll just pass it along. So what it does here is it says 2 to the power of a 6,002 digit prime. And that's just for brevity, but you could print out the whole thing if you wanted to, but by default, it,
What if you use your own exponentiation when you wrote the v the first time?
You can't exponentiate it because it's prime.
Oh,
Point, isn't it?
actually, it would check if it was prime. It would try to factor it, and it would take a while trying to figure out if it was prime.
That just happened, right? Because you defined v just as a number.
Well, then he used the built-in exponent, not his own.
Oh, that's true. It did
Yeah, no,
just
no,
happen.
But it says it's a prime, and
It did. You're right.
And it knows it's a prime because it called arithmoid, which tried to factor it. And
Yes, and that
it actually did try to factor it.
and that was the delay actually. Yeah.
Wait, but I thought you had like an upper bound. Is that is the upper bound that largest Mersenne prime?
No, that was just something from like the 70s, like the largest. It was like the largest one in the Guinness Book of Records. It was just an arbitrary one. I think the biggest one now is like it's over 10 million digits or something. So.
So your library at that point wouldn't try to factor it.
It would.
Or is there other factors? Another.
Well, primality testing is much faster
Oh,
than
it's faster.
factoring.
Okay.
Yeah.
So you can determine the number is prime much bigger than factoring a similar
Well,
number.
Probabilistic or is that?
Yeah, probabilistic.
Well, I think
There are proofs now too, they're slower.
actually, if you use the operator, it would figure out that it was a prime, but with some indirection. So.
Now, is it a guaranteed prime or is it a pseudo prime?
Well, this is definitely a prime.
That one, But
Yeah, so it did it. So
what is the
same thing.
size whether it's
It's internally in the library. I think it's actually a prime. It doesn't do like Miller-Rabin primality testing or anything. I think it is. It will actually determine if it's a prime. Okay, so see. So Graham's number. Then there's other functions. There's something called a Conway chain. I could probably skip over that. That basically, to give you an idea, this mathematician named John Conway came up with this thing called chained arrow notation, and there's some support for that in the code. And to give you an idea how fast these numbers grow, so Graham's number was shown to be between these two chains. And that doesn't seem right. That should be 4392. No, like the first number should be the same. Anyways, that's a typo. So, okay. So, and then there's something called Ackerman Functions, which, if anyone wants to look this up to get more detail about it, it's sort of like, it's kind of related to, similar to hyperoperations, but it doesn't really need them in as like nice a form, I guess. So it's harder to manipulate them. So, and so basically, I guess this will get a little bit more mathy. We're kind of done with the hyperoperation part of it. And now we're going back to like this idea of how do you handle when you're adding and subtracting these different numbers? Like, are there any insights that you can have? So one thing that came up earlier was that there is like a limit to general factorization. And this gets into the realm of cryptography and RSA numbers and that sort of things, and like unbreakable code and that sort of thing. So primarily testing is much, much easier than actually factoring, like an arbitrary, number of two composites of two primes multiplied together. So let me see. So one thing you could do is if you're trying to fiddle with a sum or a difference like that, is you want to see if there's anything in common with the values. So you take the GCD of both sides, and then you might get lucky and have the difference or the sum of what's left over and be able to factor that. And so this is an example. Like if you had to simplify this crazy thing for some reason, it's a massive, ungainly number, but the GCD is really massive, is a large portion of the expression. So if you just take the GCD and multiply it by 2, that's what your answer is. So insights like that help with, so you don't actually have to literally expand these numbers. You can just use the shorthand because it's represented canonically, and you can get quick gratification. The other thing is, after that, the idea of like detecting if a number's in like algebraic form. So for instance, if you saw that the number was in the expression passed you was in the form x squared minus 1, you could say that that's x minus 1 times x plus 1. And the interesting thing is that you can actually do this for much larger exponents, and basically split things up. It doesn't matter what the exponent is, you can still simplify it. Like say if it's an even exponent. And this would also work if you said x squared minus y squared, it would just be x minus y times x plus y. You can do it with x cubed minus 1, x4 minus 1, blah, blah, blah. And, but it would be really nice though actually if you could say, if there's a general way to factor numbers like this, if you had x to the n minus y to the n. So there's something called Cyclotomic Polynomials, which there's something come out that Gauss, the German mathematician Gauss, came up with in the 19th century. It has to do with like breaking numbers down into like the kind of like the roots of unity. And if you take for all the divisors of n, if you take the product of all the cyclotomic polynomials and multiply them, you'll get back to xn minus 1. So it has to do with kind of, like I was saying, roots of unity. But it's a really clever little identity. Now, let me see. So there's other insights into it. I could probably skip over them if anyone wants to read them. It's kind of interesting, but it's pretty mathy. Let me see. Oh, does anyone have any questions?
Do mathematicians, in fact, use this library for applications in the real world? Forget it. But I mean, are there people, combinatorialists, who do something?
I don't know. I know people download it. I haven't had any. Someone. Oh, hi. Oh, it's possible. Yeah. I think now it might be a little more likely. It's a lot more stable than it used. I think it's more useful than it had been. So it was more of like a way to learn Haskell. So I just had a project I wanted to run with that way initially.
So I have a friend who's working on a similar, like, representing really big molecular numbers library because he really wanted to, like, solve the cattle problem, which has been attributed to Archimedes. So he
Oh, that's the like Chinese remainder, the big Chi-
Exactly. I think this is like basically there's a relationship between like numbers of like different colored like.
Yeah,
categories.
I think that's all Chinese remainder,
Oh, okay.
that problem, but it's a giant,
Yeah, it's
yeah,
a
it's,
giant number. So you really wanted to like he wrote his thing in Python. So but I was wondering if that's something that you tried to like do with the library.
no, because that's a different thing where you say like the Chinese remainder theorem, like you could solve a problem where, like say you have, I don't know, you're trying to split up the bill like at the end of the night at a restaurant.
This is a different problem. This is like there's a relationship between different numbers of capital, but one of the numbers is triangular, one of the numbers is square, or something like that. And the result is like this is massive number. There's only,
Oh,
like,
that's a different one.
in, like I think the 1800s. So like the
Oh, I'm thinking of something else.
from like yeah.
Hmm.
So I mean,
I'll have to ask you about it later. Yeah, because I was thinking of something else, but yeah. Okay. So let me see. So what happens is, okay. So when you have a particular n, you've get this input that's of the form like x to the n plus minus y to the n. You can use these cyclotomic polynomials to split up the numbers and find factors. So for instance, if you had the power of 8, or I'm sorry, say the power was 8, there's 4 factors of 8, and the polynomials you get for the divisors are this. If you multiplied these together, you would get x to the 8th minus 1. And if you had numbers of that form, you would immediately have like 4 factors. So you could have this really massive, unwieldy expression, but then you could chop it down using these cyclotomic polynomials. So let me see. And I did see something in Haskell written by someone, but it kind of emphasized like this idea of the primitive roots rather than the polynomials. So I wrote this module called RF Cyclo, which I'm going to explain, and to determine actually determine these polynomials. So so there's different functions in the code that will generate these things. And this is all kind of under the hood. It is like an exposed module within the package, but you don't need to call it directly. So there's another type of factorization that a Frenchman named Aurifoy, if I'm saying his name properly, he found a way to, he found a knack for actually factoring numbers of a different form. Although it did go back to Gauss, ultimately. So this is another type of idea, except that you have to have the numbers of a certain form because they're actually taking the square root of these different things. Let me see. So you don't get like an irrational answer. You're only interested in integral factors, of course. So what happened was there was a paper written by an Australian mathematician named Richard Brent who solved for these 2 polynomials. He found a way to split this up. And then there was another class of factorizations that was developed by several mathematicians in China and Sichuan University. Excuse me. And so I implemented the algorithms in both those papers, and so that it could try to make factor numbers of those forms. So for instance, you could have a number of this form. This is from the Sichuan mathematicians paper. So it could factor something like that. So it split it up. And the interesting thing is, I guess the better thing about this library now is it, like for instance, if you were using the underlying library, you could find some of these factors, but they may or may not be prime, or they may well be composite. So in the old days, in the old version of the library, I would see this number in brackets here. I foolishly would try to have the code factor it, and you'd be waiting forever, and it was totally unusable. So at least with this notation, you know that there's a factor, and you know that it's composite, but that's kind of the end of the road. It will do other things, like if you represent the numbers this way, and somehow if you had a number, like say you were multiplying this by another number, and somehow there was a factor in common with this number, then it would check for common factors, and then take that factor out and divide down this number, that sort of thing. So it would do whatever it could but without wasting your time. The only problem is if you, for instance, want to take the number of divisors of this number, when you take the number of divisors of something, you need the exact prime factorization. So then it would give you an error so I think it's a good happy medium, because in reality no one really cares what this factors down to. But let me see. So I can probably skip over this. Yeah, so if anyone is curious, if they look up the paper, there's 1 bit in 2.7 which has the algorithm that has to be implemented. So let's see. An interesting thing is that they don't, the two approaches find different factors, and they work on different classes of numbers. So and so this is something, so this is like the example that the French mathematician found in 1871. He factored that. So you could either call it with the underlying routine, or just call it directly, and it will factor it. Oops. Sorry. So stuff like that. But when you do call the lower level function, it doesn't go any further. It just returns 2 factors, which actually aren't even they're not the only 2 factors. So you could have some remaining factors in the expression. And if you run it and it doesn't find anything, it's not of the right form, then it'll just return nothing. So, but you don't really need to go in deep anymore. But it's kind of interesting to play around with. Let me see. This goes into some pretty much heavy detail. This is the Chinese ORF is the algorithm by the Sichuan mathematicians, and that was the number that I just pumped in a minute ago. But it was called at the higher level. This is like a lower level call. Does anyone have any questions? Or let's see. So there's another thing that it will do. There is actually some overlap between the Brent approach and what I call the Chinese approach. So if you do happen to have different factors, it will actually kind of bang them up against each other and use the greatest common divisor to try to split them down into smaller factors. Let me see. Now this is something, it's getting kind of late. So this is something that's really useful. It's really like a nice shortcut when you're taking the modulus of a number. And most of the time it's not very interesting to do that, but if you're curious about what the last few digits are of a massive number like Graham's number, you can use this approach and it will figure it out. And this was something Euler came up with in the 18th century. And it's probably, yeah. Yeah, I think that's probably it. Yeah, this is a Haskell thing. It uses a lot of different pattern synonyms, view patterns throughout the code. Let's see, and I guess, yeah, to wrap things up, there were this library actually took a really long time to get working well. There's still some edge cases it doesn't handle. I had some other, I was trying to use multi-parameter type classes earlier, and they actually did not add any value at all, so I just removed them. They weren't, just caused confusion. What I'd like to do is improve the performance in some cases, maybe even use memoization. There's some library called Recursion Schemes, which is supposedly a helpful way to flatten things out. It's weird, the compilation time, if you put any optimization on, takes like 8 or 9 minutes, but I think most of the time I just ran it without any optimization, and it didn't seem to have a big impact. I would like to boost up enhance the testing with quick check. The read function would be useful. And here's some references for additional reading. These are Brent's 2 papers that I pulled from and tried to implement in the code. And this is the Sichuan 5's paper. The interesting thing is that I learned that there's this whole odd subculture called googolology, where people deal with things that are much, much bigger than this. There's some crazy guy named Jonathan Bowers who deals with like planar numbers and like 3-dimensional numbers, manifold numbers, all these crazy things that are just impossible to understand. But so it might be fun to implement some of that stuff, but just to, I don't know, for kicks. But anyways, so this is my email if anyone has any questions. I guess that's it for me. Thank you for enduring my talk.